Students, in this video we will discuss resonance energy. First of all, we will see what is the definition of resonance energy. Resonance energy is actually the energy difference between calculated and experimentally determined heat of hydrogenation of a conjugated system, right? So it is the energy difference between calculated and experimentally determined heat of hydrogenation of a conjugated system. Conjugated system like benzene. Right, students? It means resonance energy is the measurement of how much more stable is the actual structure of a compound than its extreme resonance structure. Right? So we will see how can we determine resonance energy, right? So we can determine resonance energy, that is resonance energy is equal to the calculated value, that is the calculated heat of hydrogenation, minus experimentally determined heat of hydrogenation. Experimentally determined heat of hydrogenation. Right? So by taking the difference of calculated heat of hydrogenation and experimentally determined heat of hydrogenation, we can calculate the resonance energy. Resonance energy is actually the measurement of extra stability of a conjugated system, right? Resonance energy, it is the measurement of extra stability of a conjugated system. Extra stability of a conjugated system as compared to isolated system, that means a system which have isolated double bond, as compared to isolated system. Now students, we will see how can we measure the resonance energy of benzene. Resonance energy of benzene since benzene is a conjugated system. So we will see how much more benzene is stable as compared to the system which has isolated double bond. Right? Students, we know very well benzene is stable molecule and its stability is due to delocalized pi electron. So stability of benzene is stable and its stability is due to delocalization of pi electrons. The magnitude of its extra stability can be estimated by measuring the changing in the heat of hydrogenation, right? We can measure how much benzene is more stable as compared to isolated system, right? By measuring the heat of hydrogenation of benzene, right? So we will use the following method for the measurement of heat of hydrogenation. For example, we have a molecule cyclohexene, right, having one pi bond inside, and we measure its heat of hydrogenation. Students, what is heat of hydrogenation? It is actually, we know very well, hydrogenation is an exothermic process, right? Hydrogenation is an exothermic process, though, so the heat which is released during the process of hydrogenation is known as the heat of hydrogenation, right? So heat released during hydrogenation that heat is known as the heat of hydrogenation. Right? And we know very well what is hydrogenation. It is a process in which hydrogen is added in the unsaturated compound. Addition of hydrogen to unsaturated compound is known as hydrogenation. During this process, amount of heat which is released is known as heat of hydrogenation, right? So we have a molecule, that is cyclohexene here. Cyclohexene, this is the molecule. Since there is one pi bond inside the molecule, so we need 1 mole of hydrogen, right, to hydrogenate it. So if we do the hydrogenation, cyclohexene changes to cyclohexane. We get cyclohexane, right? Now during this process, the amount of heat which is released is minus 120 kilojoule per mole, right, or minus 28.6 kilocalorie per mole, minus 28.6 kilocalorie per mole. This much amount of heat is released when we hydrogenate cyclohexene, which has just one pi bond inside the molecule, right? Now students, if we have another cyclic molecule which has 2 pi bond inside, for example, if we have this molecule, that is, this molecule is 1, 2, 3, 4, 5, 6, right? This is 1, 3 cyclohexadiene. This is 1, 3 cyclohexadiene. Students, here we have another molecule, right, that is 1,3-cyclohexadiene. Here you can see there are 2 pi bonds present inside the molecule, right? Since there are 2 pi bonds, so that's why we need 2 moles of hydrogen gas to hydrogenate it. इसके अंदर 2 pi bond मौजूद हैं, लिहाजा हमें हाइड्रोजन गैस के 2 moles चाहिए इसको हाइड्रोजनेशन करने के लिए, to convert this molecule into cyclohexane, right? After the hydrogenation, this is converted into cyclohexane. Now the heat of hydrogenation for the 2 pi bonds which are present in the molecule, it will be minus 231 kilojoule per mole. Minus 231 kilojoule per mole, or we can say minus 55.2 kilocalorie per mole. Alright students, now since the heat of hydrogenation for each double bond which is present in the molecule is 120 kilojoule per mole, the heat of hydrogenation for each double bond is, for each double bond the heat of hydrogenation is, it is approximately 120 kilojoule per mole. Now if we want to hydrogenate a hypothetical compound, right, that is 135 cyclohexatriene. What is the compound, students? Here I make the structure. This is a hypothetical compound. It means it is an imaginary compound. Since the position of pi bonds are fixed, that's why we will number the position of pi bonds: 1, 2, 3, 4, 5, 6, right? This is a hypothetical compound. Hypothetical molecule. And the name of this compound is, what are the position of double bond here? 1, 3, 5. So it is 1, 3, 5. Cyclohexa, since there are 3 triple bonds, so cyclohexatriene. Right? Now, if we hydrogenate this molecule, since there are 3 pi bonds present inside the molecule, so we need 3 moles of hydrogen gas. Hydrogen gas के कितने moles हमें चाहिए? 3 moles चाहिए to hydrogenate it to get cyclohexene. ठीक है, इसको हाइड्रोजनेशन जब हम इसकी कर लेंगे, the product which is formed is cyclohexene. Cyclohexane is formed. We know very well, for each double bond, the heat of hydrogenation is 120 kilojoule per mole, right? So this is the hypothetical compound, that is 135 cyclohexatriene, right? This compound has 3 pi bond inside the molecule. That's why we need 3 moles of hydrogen gas to convert this molecule into cyclohexane. Now, the heat of hydrogenation for 1 pi bond is 120 kilojoule per mole, right, students? For 3 pi bond, it will be 3 multiplied by 120, right? So we get here 360 kilojoule per mole. Since this much amount of heat is released, right here, so we write the minus sign here. Similarly, so this much amount of heat is released, that is minus 360 kilojoule per mole. Now students, if we hydrogenate benzene, if we want to do the hydrogenation of benzene, we know very well inside the benzene ring we have 3 pi bonds, right? So that's why 3 moles of hydrogen gas is required to hydrogenate, for the hydrogenation of benzene to get cyclohexane. This is benzene and this is cyclohexane. Then only 208 kilojoule per mole of heat is released. Kilojoule per mole heat is released, or we can say minus 49.8 kilocalorie per mole. This much amount of heat is released if we during the hydrogenation of 1 mole of benzene. Now students, how can we determine the resonance energy of benzene? We know very well. We can determine the resonance energy of benzene by taking the difference between experimental and the theoretical value of heat of hydrogenation, right? So resonance energy of benzene is equal to resonance energy of benzene is equal to experimental value and theoretical value. So what is the theoretical value? It is 360 kilojoule per mole, right? So theoretical value minus experimental value, right? What is the theoretical value here, students? It is 360, right? And minus experimental value is equal to 208. So we get the answer, that is 152 kilojoule per mole. So resonance energy of benzene is 152 kilojoule per mole. This is the amount of stability gained by benzene due to resonance. That is 150 kilojoule per mole is the amount of stability which is gained by benzene due to resonance. That's why this is known as the resonance energy. This much amount is due to resonance inside the benzene. Resonance, that's why this is known as the resonance energy of benzene. Here we can notice, students, the heat of hydrogenation of benzene is less as compared to the calculated value of imaginary compound 135 cyclohexatriene. Heat of hydrogenation of benzene is less, that is minus 208 kilojoule per mole, as compared to the imaginary compound 135 cyclohexatriene, which has minus 360 kilojoule per mole. It means that benzene has less energy as compared to cyclohexatriene. Energy of benzene is less as compared to cyclohexatriene. Lesser the energy, more will be the stability. That's why benzene is more stable as compared to hypothetical compound. Right, students? Now we will see a diagram which will make the idea more clear for the resonance energy of benzene. Now in this diagram, students, we will see here, for example, we have a molecule cyclohexene. This is the molecule which has one pi bond inside the molecule, right? And we want to do hydrogenation. Obviously it add 1 mole of hydrogen and it is converted into, right, cyclohexane. Here we get cyclohexane. Now the delta H, that is the heat of hydrogenation for this molecule, is minus 120 kilojoule per mole. Right, students? Now then the second molecule, that is cyclo-1,3-hexadiene. If we want to do the hydrogenation of that molecule, here we have cyclo-1,3-hexadiene. If you want to do the hydrogenation of this molecule, since there are 2 pi bond, so we need 2 moles of hydrogen gas, right, to convert this molecule into cyclohexane. To convert it to cyclohexane, right? So delta H for this molecule will be minus 231 kilojoule per mole. Now students, the hypothetical compound, if we have hypothetical compound like cyclohexatriene, if you want to do the hydrogenation, it has 3 pi bond inside, right? 1, 2, 3, 4, 5, 6. 135 cyclohexatriene. 3 pi bonds are there, so we need 3 moles of hydrogen gas to hydrogenate it and convert it into cyclohexane. Convert this molecule into cyclohexane, right? So the delta H for this molecule will be, that is heat of hydrogenation for this molecule will be minus 360 kilojoule per mole. On the other hand, students, if we have benzene molecule, and we want to do hydrogenation of benzene, 3 pi bonds are there, so 3 moles of hydrogen gas is required, right, to convert benzene molecule into cyclohexane. Then the delta H for this molecule will be minus 208 kilojoule per mole. Right, students? Now what is the resonance energy, students? It is the It is a difference between the theoretical value as well as the experimentally determined value of the heat of hydrogenation, right? So we will take the difference here, we will take the difference between the experimentally determined heat of hydrogenation as well as the theoretical value of heat of hydrogenation of cyclohexatriene. That is, what is the heat of hydrogenation of cyclohexatriene? It is 360 kilojoule per mole, right? So we will take the difference here, 360 minus what is the heat of hydrogenation of benzene, 208. It would become 150 kilojoule per mole. That is 152 kilojoule per mole. 152 kilojoule per mole. It means this is the resonance energy of benzene. That is 152 kilojoule per mole. This is the resonance energy. Resonance energy of benzene. It means benzene is this much stable as compared to the hypothetical molecule. I hope you got the concept, students.